Today, we meet one of the most beautiful and, at first, most mind-bending ideas in all of programming, recursion. Recursion is when a function calls itself. The first time you hear that, it sounds almost like a paradox and 8212. How can something be defined in terms of itself without spinning forever? But recursion is not a click or a curiosity. It is a genuinely powerful way of thinking, and it unlocks whole families of problems that are clumsy or nearly impossible to solve any other way. An 8200, searching, sorting, walking through trees, divide and conquer. The core idea is wonderfully simple. Once it clicks, you solve a big problem by shrinking it, step by step, into a smaller version of the very same problem, until you reach a version so tiny that the answer is obvious. So let us take the mystery out of it, and by the end of this class, recursion will feel not confusing but elegant. Here is what we will understand today. First, what recursion actually is. Second, the two essential parts that every recursion must have. Third, the base case, and 8112, the part that makes it stop. Fourth, the recursive case, and 8112, the part that shrinks the problem. Fifth, the call stack, which is what is really happening behind the scenes. And sixth, how recursion compares to plain iteration, an ordinary loop. Let us begin. Let us pin down the idea precisely, because a clear definition removes most of the confusion. Recursion is a function that solves a problem by calling itself an 8212. But, and this is the crucial word, it calls itself on a smaller version of the same problem. Not the same problem again, which would loop forever, but a genuinely smaller one. Each time the function runs, the problem it faces gets a little bit tinier. Think of it like a set of Russian nesting dolls. To open the whole set, you open the biggest doll, and inside you find the same task, an 8200 8200 tool. Open a doll 8200 200 200 8200 tool. You keep applying the exact same action to smaller and smaller versions until you reach the tiny solid one at the center that does not open. Recursion is that the same action applied to ever smaller versions until you hit the smallest one. The mental shift is to stop trying to trace the whole thing at once. You do not need to picture every level in your head. You just need to trust two things: that the problem is getting smaller each time, and that eventually it gets small enough to answer directly. So, the takeaway: recursion means a function calls itself on a smaller version of the problem, shrinking it each time until the answer becomes obvious. Hold the nesting dolls picture, and the rest follows. Every correct recursion, without exception, is built from exactly two parts. If you can spot these two parts, you can read any recursion. If you can write these two parts, you can write any recursion. The first part is the base case. This is the simplest possible version of the problem, an 8200, so simple that you can answer it directly with no further recursion. It is the place where the shrinking stops. Without a base case, the function would keep calling itself forever, because nothing ever tells it to stop. The second part is the recursive case. This is where the function calls itself, but on a smaller input than it received. It is the step that does the shrinking and 8212, taking the current problem and reducing it, then handing that smaller problem back to the same function. And here is the key relationship between them. You need both, and they work as a pair. The recursive case keeps making the problem smaller. The base case catches it when it finally gets small enough and stops the chain. Miss the base case and it never ends. Miss the recursive case and it never actually does any work. A stop and a step. So the takeaway: every recursion has exactly two parts, an 8200 half, a base case that stops it, and a recursive case that shrinks the problem, an 8200 half, and both must be present for it to work. Let us look more closely at each part, starting with the base case, because it is the one beginners most often forget, an 8200, and forgetting it is fatal. The base case is the smallest input your function can answer without recursing at all. It is the anchor, the floor, the point where the function says, I do not need to call myself for this one n8225. I already know the answer. For a function that counts down, the base case might be when you reach 0, stop. For one that sums a list, it might be an empty list sums to 0. Now feel why it is so critical. Every recursive call is a promise that the problem is getting smaller and heading somewhere. The base case is that somewhere. It is the stop sign at the end of the road. If there is no base case, or if the shrinking never actually reaches it, then the function calls itself, which calls itself endlessly and 8208. And the program does not just give a wrong answer, it crashes. So the discipline that experienced programmers follow is to write the base case first, before anything else. Ask yourself, what is the very simplest version of this problem, and what is its answer? Answer that, and you have laid down the anchor that makes the whole recursion safe. So the takeaway, the base case is the smallest input you can answer directly, and it is the stop sign that ends the chain of calls and 8212. Write it first, because without a reachable base case, the recursion never ends. Now the other half ain't 8212, the recursive case, the part that actually does the shrinking and moves us toward that base. It begins with the big problem. The full input, the function was handed. The recursive case then calls the function again, but on a smaller problem, and 812 one step less, one item fewer, one level down. It does whatever small piece of work belongs to this step, and delegates the rest of the work to another copy of itself running on that reduced input. It is saying, I will handle this one layer and trust a smaller version of me to handle the rest. And here is the non-negotiable rule that ties back to the base case. Every recursive call must move closer to the base. If your function is supposed to count down, but you accidentally keep it the same, or make it larger, it will never arrive at the base case, and you are back to infinite calls. The direction of travel must always be toward the stop sign. Smaller, 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 and 82 are full, until base. So the takeaway, the recursive case calls the function on a smaller input and does one step of the work, and crucially, every such call must move closer to the base case and 8212, or the recursion will never arrive. Ideas become clear with a concrete example, so let us walk through the classic one, factorial. The factorial of a number is that number multiplied by every whole number below it, and it has a naturally recursive shape. As for factorial of 3, the recursive case says, factorial of 3 is 3, multiplied by factorial of 2. So, to answer 3, we first need the answer to a smaller problem, factorial of 2. Factorial of 2, in turn, is 2 multiplied by factorial of 1. Again, to answer this, we need an even smaller problem solved first. Notice how each step is the same rule, applied to a smaller number, exactly as we described. Factorial of 1 is our base case and 8212. The answer is simply 1, no further recursion needed. We have hit the floor, and now the magic reversal happens. With factorial of 1 known to be 1, we can finish factorial of 2 as 2 times 1, which is 2, and with that, we can finish factorial of 3 as 3 times 2, which is 6. The calls went down to the base, and then the answers multiplied back up. So the takeaway, factorial of 3 asks for 3 times factorial of 2, which asks for 2 times factorial of 1, which is the base case, 1 and 8212, and then the results multiply back up the chain to give 6. Down to the base, then back up with the answer. That back up the chain is not magic, and 812, it is a real mechanism your computer uses. And understanding, it makes recursion concrete. It is called the call stack. Every time a function calls another function and 8212, including itself and 8212, the computer stacks that new call on top and pauses the one underneath. So when factorial of 3 calls factorial of 2, the call for 3 is paused and sits there waiting, while factorial of 2 goes on top and starts running. Then it too pauses and stacks factorial of 1 above it. The calls pile up, each one frozen midway, waiting for the answer from the call above it. The base case is what breaks the pile up. Factorial of 1 does not stack anything new and 82112. It just returns its answer, 1. That is the bottom of the descent, the first call that actually completes. And now, the stack unwinds. With factorial of 1 finished, the post factorial of 2 can resume, finish its multiplication, and return. That lets the post factorial of 3 resume, finish, and return the final answer. The calls resume in reverse order, from the base back up to the top. That is exactly the back up the chain we saw. So the takeaway, every recursive call is stacked and paused, waiting on the one above it. The base case returns first, and then each pause call resumes in turn, unwinding the stack from the base all the way back up to the original call. Now that you can see the stack, you can understand exactly how recursion goes wrong on A212, and it is worth burning this in, because it is the #1 recursion bug. Correct recursion looks like what we just saw. Every call shrinks the input, so the chain of calls marches steadily toward the base case, hits it, and unwinds cleanly. The stack grows for a while, then empties. Everything is fine. Runaway recursion is what happens when the calls never reach the base case and A2, 200 and 200. Maybe you forgot the base case entirely, or your recursive step does not actually make the problem smaller. Now, the stack just keeps growing. Call after call piles on, none of them ever returning, because none of them ever hits the stop sign. The computer's call stack is not infinite in A2 or 12. It has a limited amount of space, so eventually it fills completely, and the program crashes with an error you will absolutely meet in your career, a stack overflow. When you see that error, this is almost always the cause of recursion that never reaches its base. So the takeaway, correct recursion shrinks toward a reachable base and unwinds cleanly. But if the base is never reached, calls pile up until the stack runs out of space and the program crashes with a stack overflow. A fair question at this point is, if a plain loop can repeat things too, when should I actually use recursion instead of iteration? Let us compare them honestly. Recursion is at its most elegant when a problem naturally contains smaller copies of itself, and A212, especially nested or branching structures, walking through a family tree, exploring folders inside folders, or divide and conquer algorithms that split a problem in half again and again. For these, recursion expresses the solution almost as simply as you would describe it in words. Iteration and A212. An ordinary loop, and A212, is often the better choice for flat, straightforward repetition. Counting through a list. Running something a fixed number of times, a loop is usually simpler to read, and it is lighter because it does not pile up calls on the stack. There is no risk of a stack overflow with a plain loop. And here is the honest truth that surprises beginners. Anything you can do with recursion, you can also do with iteration, and vice versa. They are equally powerful. So the real decision is about clarity and 8-12 volt. Which one makes your particular solution read most naturally? Choose recursion when it makes the code clearer, and a loop when that is simpler. So the takeaway, both recursion and iteration can solve the same problems. So pick the one that reads clearly and 8-12 well. Recursion shines on nested, branching problems like trees, while a simple loop is often best for flat repetition. Let us close with a short set of habits that will keep your recursion correct and readable from the very start. First, reach for recursion when a problem contains smaller copies of itself. That is the signal. If you can describe the problem as solve a smaller version of this, then combine. Recursion will usually be the cleanest expression of it. Second, always write the base case first, before you write the recursive step. Deciding where and how it stops upfront forces you to be clear about the anchor and A212, and it is the single best way to avoid the infinite recursion trap. Third, before you trust your recursion, check every path through it and confirm that each one shrinks toward the base case. Trace what happens on the smallest inputs. If there is any route where the problem does not get smaller, you have a stack overflow waiting to happen, and 8212. Fix it before you run it. So the takeaway, use recursion when a problem nests inside itself. Always write the base case first and verify that every path shrinks toward that base and 8200. Do those three things and your recursion will be both correct and clear. Let us gather the whole class in one breath. Recursion is a function calling itself on a smaller version of the same problem. It always has two parts, an A2-1 pull, a base case to stop, and a recursive case to shrink. The base case is the smallest input, answered directly, and A2-2 the stop sign that ends the chain. The recursive case must move closer to the base with every single call. The call stack holds the paused calls, then unwinds from the base back upward. And a base case that is never reached means infinite calls and a 200 stack overflow. Next class, ANE ET112. Recursion in action, searching and sorting by dividing the problem, one ID at a time. That is recursion in A2112, not a paradox, but a discipline. A base case to stop, a recursive case to shrink, and a call stack quietly keeping track of it all. It feels strange for exactly as long as it takes to click, and then it becomes one of the sharpest tools you own, opening up trees, searches, and divide and conquer problems that would be painful any other way. Write the base case first, make every step smaller, and trust the shrink. We will see you in the next class.